Okay, we're starting Chapter 7 in the trigonometry textbook. Chapter 7, you can see, is on applications of trigonometry and vectors. Now, vectors, the book discusses in these last two sections, but we're actually going to skip vectors because I've got a whole dedicated playlist on vectors, which will include everything that would be taught in these sections. So if you want to learn about vectors, go check out that playlist. So these first three sections are what we're going to be going through in this playlist from Chapter 7. And these sections are on applications of trigonometry. And so specifically, what we're going to use trigonometry to do in these three sections is we're going to come up with equations that will allow us to solve any triangle, not just right triangles. So we know from Chapter 2, using just the definition of trig functions, that assuming we have some information about a right triangle, information in terms of we know some angles and some side lengths, then we're able to use trig functions to solve for all three of the angles and side lengths. If angles involved are special angles, then we can evaluate the exact trig function manually. But even if we're not dealing with special angles, we can use our calculator, which does highly accurate numerical approximations of trig functions for any angle. So again, we learn how to solve any right triangle, assuming you had at least some information to start with, right? Because otherwise, if I gave you a triangle and said, solve this triangle, well, you can't solve it. There's not enough information. It's kind of like asking someone a question, but only giving them half of the question. There's not enough information, right? Okay, and so what we're going to develop that will allow us to solve any triangle is the law of sines and the law of cosines. And we're going to start by taking a look at the law of sines. Now, the law of sines is going to be a little more challenging to learn because of this ambiguous case of the law of sines, which there's no ambiguous case when it comes to the law of cosines. So let's get started with this opening section, and as we progress, you'll see what I mean by this ambiguous case and where it comes from. All right, so here's the opening image in this chapter. And yeah, so here's, I mentioned this many times when we were solving triangles in Chapter 2, looking at different applications of solving right triangles. And it's these devices that surveyors use. And I'm not a surveyor, but from what I've gathered, these devices, the main use is that they're able to get accurate angles between features, even if those features are far away. And so you can get these angles and then combine that with lengths that you're able to manually measure. And then with the combinations of angles and lengths that you have, you can use your ability to solve triangles to find the rest of the angles and lengths, where you can think about one of those lengths that you find might be difficult or impossible to measure. So an interesting example was you had like Mount Everest, and then there was the ground level, and then there was like another peak that was a certain way up. Maybe that was high enough to where you could actually get a view of the peak between the clouds or something like that. And so you can think about, they were able to, from the ground level, they could measure this distance manually, right? And they got one of these survey devices up here, and they could see the peak. And so they could use this device to get the angle between the horizontal from where they're located and the peak. They got this angle, okay? Then you've got, that's a right triangle there, and this extends all the way down. Now, so they've got this length. They've got this length here. They've got this angle. And so from there, you can use trigonometry to get this length, and even this length if you wanted it. Okay, but they know the height that they hiked up, so they add that to this, and you can get the height of Mount Everest without having to actually climb it. Right, but in Chapter 2, we only solved right triangles. And as you can imagine, for surveyors and other applications, not just surveying, you want to be able to solve any kind of triangle, not just a right triangle. And so that's the goal of this chapter. And something else that's interesting is that it says, so surveyors use a method known as triangulation to measure distances when direct measurements cannot be made. due to obstructions in the line of sight. So yeah, this idea of, you think about triangulation, like the CIA pinpoints the location of a cell phone. So I guess you know the distance from the cell phone to the tower, the cell tower. And so you have that distance, you can get in their angle. What they're doing with triangulation is they're solving triangles to get distances to get unknown distances that are hard to measure, and then they can pinpoint locations. That's the idea of triangulation. You're solving triangles. Okay. So, congruency and oblique triangles. We now turn our attention to solving triangles that are not right triangles. To do this, we develop new relationships or laws that exist between the sides and angles of any triangle. The congruence axioms assist in this process. Recall that two triangles are congruent if their corresponding angles, sides and angles are equal. So yeah, remember congruence from geometry. It's like saying that two triangles or two figures are equivalent. And so like these two triangles are equivalent and are congruent. And that just means that, you know, they're oriented differently. They might look different visually, but the idea with congruence is that you can take any figure and you can reorient it in 3D space, flip it into and out of the page, spin it, whatever you want, but you just can't change the size of the figures. But by purely reorienting them, if you can line them up one on top of the other and it's a perfect alignment, then those figures are congruent. And so the meaning of that is like the corresponding sides and the corresponding angles are all have equal lengths and equal measures. That's the idea. Okay, and so now they want to go over the congruence axioms here that we learned in geometry. Now, why are we doing this here? Well, because you can think about, when it comes to thinking about solving triangles, so finding all the side lengths and the angles, well, there's going to be a minimum amount of information you need to be able to solve the triangle, right? Like you can't, again, I can't just say, okay, here's this triangle. We don't know any of the angles or lengths, and I'm going to give you that length B is 3. Now solve the triangle. Well, you can't solve the triangle. That's not enough information. And the way you can think about how do you know if you have enough information to solve a triangle? Well, you can think about what's required for congruence. The idea is so we knew that there was the side angle side congruence axiom. If you knew the length of two sides of a triangle, or no, it was if you can compare two triangles and you said that two sides were the same length and the angle between those two sides was the same measure, then those two triangles were congruent, right? That was the congruence axiom. So, but another way, if you look at that from another perspective, what you're really saying is that if you, with one triangle, once you fix two side lengths and an angle between those side lengths, then the triangle is fixed. In other words, you've fixed all of the other angles and side lengths. You might not know what they are, but they're fixed. And you can think about why that makes sense. It makes sense because I can't say two triangles are congruent by just specifying one side, or by just saying that two of the corresponding side lengths have equal length. Because with that, I have the ability to arbitrarily change other side lengths of another. How can I say they're congruent if there's still ambiguity regarding side lengths and angles, right? So again, it makes no sense to say that two triangles are congruent if all of the angles and side lengths of both triangles aren't fully constrained, you see? And so to show congruence, these were the three axioms. If you could show that two side lengths and the included angle were the same between two triangles, then that meant the two triangles were congruent. If you could show that two angles and the included side length were the same between two triangles, then they were congruent. If you could show that all three sides were the same side length, then the triangles were congruent. Okay? But like, for example, if you could show that between two triangles, if you could show that all three angles were congruent, well, that doesn't prove congruence of the triangles, because I can draw right now two triangles that have the same angles. Those are similar triangles. You can take a triangle and scale it up or down its size without changing the three angle measures, right? So there's no congruence axiom there. And that's why it makes no sense to say solve a triangle given three angles. If I give you three angles of a triangle and that's it, and I say solve the triangle, well, that question, there's not enough information because the side lengths, it's ambiguous. I can't give you, the side lengths could be a bunch of different things. There's an infinite number of triangles that would satisfy that criteria. Okay. Now, they give a reminder here that the three angles of a triangle sum to 180. And so they point out that if you have a situation where you have a side and two angles, but the side is not included between those angles, then you still automatically, because you have two angles, you have the third angle, so you can convert this to the angle side angle condition, right? Okay, and so with that, they state how there's three cases where you have enough information to where the triangle is fully constrained and you can consider solving it. Side, angle, and side, side. The three congruence axioms. With side, angle just being another version of angle, side, angle, because you can convert it to that. Okay. And so this is what we need to develop these laws using trigonometry around. When we have information along these lines, when we have enough information, given information pertaining to these three scenarios, how can we use trigonometry to solve any triangle? Okay, so a triangle that is not a right triangle is an oblique triangle. So yeah, that's good to note. If you either have a right triangle or you have an oblique triangle. If it's not a right triangle, it's oblique. So like you have right triangles, you have acute triangles, you have obtuse triangles. Acute triangles have all acute angles. Right triangles have one 90-degree angle and two acute angles. Obtuse triangles have one obtuse angle and two acute angles. But obtuse and acute triangles are both fall under the category of oblique triangle. All right, so recall that a triangle can be solved, that is, the measures of the three sides and three angles can be found, if at least one side and any two other measures are known, whether they be angles or side lengths. So yeah, that's another way you can sum up this statement here. The side, angle, side, and side, or even the side, angle. You can state that this way, that if you know at least one side length and then pick any of the other two measures, whatever one, two angles, two sides, an angle, whatever, then you can solve the triangle. That's kind of a condensed way of saying the minimum amount of information you need to be able to fully constrain a triangle to where you can think about actually solving it. Again, I want to note in the sense that it makes no sense to give someone three angles of a triangle and say solve the triangle. Because there's which triangle? There's an infinite number of potential triangles. There's no unique answer to that. Okay, now, so what they do next is they list out these cases where we can solve the triangle. So you can see, all right, case one is the side, or no, the angle side angle, which is also side angle, right? If you have side angle, then you automatically have angle side angle. So there's that case. Case 3 is the side angle side, and case 4 is the side. But they have this extra case in here, the side angle. So what's this about? Because that's not included here. Well, the side angle does mean that the triangle isn't fully constrained. Yes. However, this is a special case where it's not like there's not an infinite number of possibilities, though, like the angle case would be. The side angle case, yes, it's not fully constrained, but we have enough information to where we can, there's only like a few possibilities. And actually, in some situations, there is only one unique triangle, depending on the angles and the side lengths okay? But any other scenario outside of these four cases, like angle, it's too ambiguous, you can't think about solving it. Okay, so now here they mentioned the angle means similar triangles, and we can't solve it with just given three angles, right? Okay. Solving a triangle with given information matching case 1 or case 2 requires using the law of sines, while solving a triangle with given information matching case 3 or 4 requires using the law of cosines. Okay, so if we come back here, the case 1 and case 2, we're going to use the law of sines. And in the next section, this is the ambiguous case of the law of sines. That's the title of the next section. So we're really going to focus on this in the next section. But we are going to touch on these kind of cases in this section as well, though. and in the example problems. But we're really going to dive into this case in full in the next section. Okay, but again, there's no ambiguity here. With these cases, the triangle is completely constrained. So you're going to get one unique answer for all of the angles and side lengths. Okay, so the derivation of the law of sines. To derive the law of sines, we start with an oblique triangle, such as the acute triangle in figure 1a or the obtuse triangle in figure 1b. So, okay, we've got an acute triangle, all acute angles here, and an obtuse triangle. Here's one obtuse angle. Now, note with triangles, I think we talked about this in chapter 2, but there's a labeling convention that you want to use with triangles. You want to label the vertices, which correspond to the angle measures, as A, B, and C, and you can pick which one is A, which one is B, which one is C. It doesn't matter. You pick. But the side length opposite of like angle A is going to be lowercase a. The side length opposite of angle C is going to be lowercase c. Opposite B is going to be lowercase b. So this side length would be lowercase b. You always want to use that convention with triangles in geometry and trigonometry. Okay, and you can see the same thing over here. Angle A, side length A, etc. Okay, and now you can also notice that these two triangles cover all possible cases of triangles outside of a right triangle, but we don't need to do right triangles. So this covers all cases of oblique triangles. Okay, now first construct the perpendicular from B to side AC or its extension. All right, so we're going to go from B, drop a perpendicular, which we can do, right? We can't necessarily drop a perpendicular bisector so that it bisects this and it's perpendicular, unless it's for just a random, completely general triangle. But we can drop a perpendicular, that's fine. Call the height h. Okay, now to drop a perpendicular within obtuse triangle, depending on what perpendicular you're dropping, in this case, you can still do it. You just have to do like a virtual extension of this side length. But that doesn't mean that this is side length B. This side length, the side length B is still just this. Okay, but like for an obtuse triangle, like in this case, you don't have to do like a virtual extension. Okay, so we dropped a perpendicular from vertex B, called that H, that length H. We did this for both triangles. Okay, then C is the hypotenuse of the right triangle ADB, and A is the hypotenuse of right triangle BDC. So ADB, C is the hypotenuse of the right triangle. BDC, A is the hypotenuse. Same thing here. ABD, C is the hypotenuse. DBC, A is the hypotenuse. Okay. Now, in triangle ADB, sine of A would be H over C for both triangles. Okay, so they do that and then solve for H. In triangle BDC, sine of C is H over A. For both triangles, they solve for H. Then they set these two H's equal, and they get this. A sine of C is equal to C sine of A. And now from here, you can divide both sides by sine of C and sine of A and get this, or you could divide both sides by A and C, and like you could flip these, and you get the same relation. Okay, and now you can do this exact same process, dropping a perpendicular from angle C to side C and angle A to side A for both triangles, and you get two more relations. Okay, and just note that this was completely general for both triangles. So these relations apply for an obtuse or acute oblique triangle. They also apply for a right triangle, but we don't need it because we can just use trig functions. But with a right triangle, these would like simplify to regular trig functions. But so these relations apply for any triangle, no matter what kind it is, absolutely any triangle. And so that's the law of sines, these three relations, which you can actually summarize with a triple equality here. What the law of sines is saying is that if you take the ratio of the sine of an angle and the side length opposite that angle, that ratio is constant for any angle side length pair. And it doesn't matter, like if you're dividing with the side length in the numerator and the sine of the angle in the denominator, it doesn't matter as long as you're consistent. So again, the law of sines is you have any triangle and you pick a pair, an angle pair and the side length opposite that angle. You pick a pair, and you take the sine of the angle and the side length, and you take the ratio of those two, and however you want to take the ratio, side length in the numerator, sine of the angle in the denominator, whatever. That's going to be a constant for any angle side length pair. That's a constant. That's what the law of sines tells you. Okay, but again, it doesn't matter. You can put the sine of the angle in the numerator. It doesn't matter. Just be consistent. And again, this applies for absolutely any triangle. But if you did it with a right triangle, you're just going to end up with regular trig function relations. Okay, so now when you think about case 1 here, side angle, 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 side angle. So let me. Okay. To use the law of sines, you can't just arbitrarily have just any angles and side lengths. It needs to kind of match up with side lengths and angles being opposite of each other. Because, for example, case 3, side angle side. So that would mean that we have side length C, for example, side length C, side length B, and angle A. Okay, so we have angle A. We could take the sine of A. But now we have to divide that by the side length A, okay? Now we want to pick another pair, angle, side length pair, but we don't have another angle, right? We only had C, B, and A. So, I mean, I guess since we have B, I could use that, but we don't have angle B. We don't have side length A. So that's one equation, 2 unknowns. You can't solve case 3. And then obviously case 4, you can't solve either because all you have is side lengths. You need each of these equalities has two angles in it. Okay, but if with the side angle, which automatically means you have angle side angle. So let's say we had angle A, B, and side length C. That's the side length included between the two angles. Well, first of all, because we have two angles, that means we automatically have angle C. Okay, so we need to solve for either side length B or side length A to start. So we can say, so we have angle A, all right, we're looking for the side length A, but we have angle C, and we have side length C, so there you go. One equation, one unknown, we just need to solve for A, and we're going to get one unique answer for A. And that's how case 1 is always going to work out with the law of sines. Okay, but now let's look at case 2. Let's think about case 2 as an example. So side angle, but you don't have the included angle. So that would be like we've got side length C, side length A, and either angle A or C. So, okay, let's say we have angle A, sine of A, and we have side length A. That's good. Okay, but we can't solve for any other angles because we only have one angle. So we have side length C, so let's do sine of C over C. Well, okay, that's not so bad. We've got one equation, one unknown. We know sine of A, we know side length A, we don't know sine of C, but we know side length C, so we got one equation, one unknown. So what's the problem? Well, the problem is we're going to solve for angle C, but we're going to have to take the inverse sine of both sides of the equation, and we know that when you do that, it's like taking the square root of both sides of an equation. You have to put the plus or minus. You have to consider, there's multiple numbers when squared that equal this number. Well, there's multiple angles. When you take their sine, you get what the argument is. Okay, now, but when we solved trig equations and having to use introduce inverse trig functions, we always got an infinite number of answers. But you can think about here, it's not going to be an infinite number of possibilities because, okay, angle C can't be negative, so it's not going to be a negative angle, and it can't be anything greater than 360, right? So, well, in that case, we know that in general, there was two possibilities for the angle that answered the inverse trig function question. There was two angles between 0 and 360. That answer the question of the inverse trig function. What angle, when you take this trig function, you get the value. Now, there were certain quadrantal angles that were special cases, like inverse sine of 1. There's actually only one angle. When you take its sine, you get 1. That's 90 degrees. But in general, there was two angles you have to think about between 0 and 360. And so that's how the ambiguous case of the law of sines comes into play. And again, this doesn't happen for any of the other cases where you're able to solve the triangle. There's no ambiguous case of the law of cosines. It's just for this scenario where you know two side lengths and an angle that's not included between those side lengths. You can solve that triangle using the law of sines, but there's cases where it's going to be ambiguous. In other words, your final answer will be, okay, here are these angles, these side lengths, but side length A could be either this or this. And that's how you solve the triangle. Now, just to note, and we're going to get into full detail on this in the next section, but the ambiguous case, sometimes it's not ambiguous. It might end up being the case that with the side lengths you're given and the angle you're given, there's only one possibility for the other side length. So it's actually not ambiguous. There's other cases with case 2 here where you're given two side lengths and an angle, and actually there's no possible triangle. It's impossible to have those constraints. And again, there's other cases where you're going to have to specify two potential side lengths for one of the sides. But again, just to note, these other case 1, case 3, and case 4, it's always completely unique. Once you're given this information, side, angle, side, angle, side, or side, everything's fixed. There's one unique answer for all the values of the triangle. Okay, but again, we're going to go into full detail on this ambiguous case in the next section. Okay, so now they give some examples of applying the law of sines, and we'll work a bunch of example problems. It's pretty straightforward if you have the side angle, or angle side angle case. Yeah, it's pretty straightforward. It's one unique answer, but we'll still work a bunch of examples. So they're given angle A, angle B, which means they automatically have angle C. They have side length A. So you set up the law of sines. You're going to have one equation, one unknown with one unknown side length. You're not introducing any inverse trig functions, right? Sine of 32 is one unique number. Sine of 81.8 is one unique number, so you can solve for B. So now you've got side length A, side length B, and two angles. They get the third angle here, but it might be the case that you need to solve for the third angle from the start. But in this case, they didn't need to do that. Then they just use the law of sines again, right? Once you've got like a fourth or fifth value, then you're home free. Then there's really going to be no issue with using the law of sines. So they just pick a side length angle pair, a couple of those, and solve for side length C, and they're done. Okay, here's a more practical example. So you've got this person wants to measure this distance across a river. They're able to, I guess that's their camp or something, they're able to measure the distance from camp to the side of the river. They're able to figure out the angle between that position at the side of the river and right across the river from that position, this angle, and they're able to measure this angle as well. So that's an angle side angle case. So you can get, well, you're not trying to solve the whole triangle here, you're just trying to solve for this value. But you can get this angle if you need it, because you have two angles. And it's the angle side angle case. You can do this angle, sine of this angle divided by the side, what you're looking for, the river length, the river width. Then you can do the sine of this angle, that's equal to the sine of this angle divided by the length that you measured. And then solve for this length, that's going to be one unique value. Okay, so now here's another example. It's just another angle side angle example. You know two angles of a triangle and a side length. So the law of sines is straightforward and easy in that case. Since you can easily get that third angle, you're home free. All right, the area of a triangle. So what they do here is they use trigonometry to come up with another formula, an alternate formula to 1/2 base times height for the area of a triangle, which is really useful because different scenarios have different constraints, right? And it might be the case where it's difficult or impossible for you to figure out what the height of a triangle is, or even its base corresponding to a height. But with another formula, you could get the area of that triangle with a formula that kind of uses different parameters. So, okay, so yeah, area is 1/2 base times height of a triangle, where the height is, there's three different options for the height. You're just dropping a perpendicular from a vertex to the side opposite that vertex, and you could do that, right? No problem. This would have a different height than this, but you would say 1/2 times the length of C, not the length of AC here, the length of C times that height. Here would be 1/2 times H times that length Or you could do, that would be like the perpendicular, 1/2 times that length times the length of A. All three would result in the same value. And actually, I don't think I drew this right. These three lines should all meet at the same point. But you get the idea. Okay, so they draw this perpendicular here, this height, and then they say, they do the same thing over here because we want to consider an acute and obtuse triangle to make it completely general. Then they say consider triangle ADB. So here's ADB. All right, the sine of A is going to be H over C for both cases. So H is equal to C sine A. And then they just substitute this H into the area is equal to 1/2 base times height formula. And they get the area is equal to 1/2 B times C times sine of A. So 1/2, this is B times C times sine of A. And you can do this same procedure using the three different heights. And what you find is that, they do this for the three different heights and they get these three formulas here, but you don't have to memorize these. The pattern is that you just take, notice the height is not included in these formulas. There's no height here. It's a pure function of side lengths and one angle, which is really cool. So all you have to do is you say the area of any triangle is 1/2 times the product of any two side lengths you want times the sine of the angle between those side lengths. That's it, right? So 1/2, and it's for an acute or obtuse triangle, or even a right triangle if you want. 1/2 B times C times sine of A. B times C times sine of A. 1/2 A times B times sine of C. A times B times sine of C. A times C times sine of B. A times C times sine of B, see? But like with a right triangle, if you choose to where the center angle is 90, sine of 90 is 1, so you just get the original 1/2 base times height formula. So that's pretty cool. All right, so now they work some examples, but we'll work example problems on finding the areas of triangles in the next video.